Hello everyone, welcome back to Cambridge Guru once again. In the last video, we did some questions based on uh, plotting the set of points in an Argand diagram, and we also did some questions on finding out the maximum and the minimum value of complex number which is lying in an Argand diagram, right? Uh, Let us do some more questions, some more examples that Cambridge asked in the final exam, and as you can see that I have taken all the questions which come in your final exam, final board exams, right? So all these questions which I am going to take today, they are not basically based on plotting the points and finding out the region least and finding out the least and greatest distance, but another variety which involves finding out the modulus, what is the real part, what is the imaginary part, right? So let us do this quickly. So next example says that the complex number z is given by 1 plus cos 2 theta plus I sine 2 theta, and where theta is lying in this interval, we have to show that the modulus of z is 2 cos theta and argument is just theta, right? So as you know that modulus of z is given by squaring and adding and then taking out the square root of real and imaginary part. So mod of z is given by 1 plus cos 2 theta whole square plus sine 2 theta whole square, right, and square root, right? This is your modulus. So opening up the bracket, this is 1 plus cos square 2 theta plus 2 cos 2 theta plus sine square 2 theta. Please do not square these 4, means it won't become 4 theta square, right? And we do not square the theta, we square the function sine square theta. Basically it is sine 2 theta into sine 2 theta, right? So this is the square root. Now 1 plus cos square 2 theta, as you can see that cos square 2 theta is here and sine square 2 theta is here. Since 2 theta angles are same, so I can replace this plus this as 1, right? So this initial one is as it is, and replacing these two terms with just another constant which is 1, and then 2 cos 2 theta is the remaining part, square root, right? So cos square theta plus sine square theta, using that identity I have written this as 1 right? Now adding this, 1 plus 1 is 2, so this is 2 plus 2 cos 2 theta, sorry, so many 2's are there, do not get confused. So 2 plus 2 cos 2 theta, taking out 2 outside as a common factor, you remain with 1 plus cos 2 theta inside the bracket with the square root sign, right? Now using the double angle formula for cos, which says that cos 2 theta is 2 cos square theta minus 1, right? So replacing this 1 plus cos 2 theta is 2 cos square theta, what I'll get is mod z is 2, this is again multiplied by 2 cos square theta, right? Replacing the double angle with the half angle formula, right? So 2 cos square theta and square root, right? So this is 4 cos square theta with a square root. So mod of z is equal to just 2 cos theta, right? And this was asked in the question, that show that modulus of z is 2 cos theta, and then argument of z we have to prove as theta, right? So argument means tan inverse of the imaginary part. As you can see that as you know already, that argument of a complex number z is tan inverse imaginary part of z divided by real part of z, right? So imaginary portion in our question is sine 2 theta and real part is 1 plus cos 2 theta, right? So again using the double angle formula, this time we have to replace this sine 2 theta with 2 sine theta cos theta, right? 2 sine theta or 2 cos theta sine theta, right? This is a double angle formula for sine 2 theta. So this is tan inverse 2 sine theta cos theta divided by 1 plus cos 2 theta is 2 cos square theta, right? Okay. Now, this 2 can be cancelled with this 2. 1 cos theta can be cancelled with 1 cos theta here. So, you will remain with just tan theta inside the bracket. So, my final answer for argument of z will be tan inverse tan theta, right? And tan inverse tan theta is basically theta. So, argument of z is just theta. Okay, so this is the answer as far as your first part is concerned, and second part is that we have to prove that the real part of 1 upon z is constant. Now before doing this, just remember one identity that I told in the introductory chapters, in the introductory lecture of this complex number chapter, was that z into z conjugate is mod z whole square. Why we have to use this identity in this particular question? Because if there is any complex number which is in the denominator, we have to bring that complex number in the numerator by multiplying the complex number with its conjugate, right? Both numerator and denominator. So basically, if it is 1 by z, so we have to multiply with its conjugate like this. Okay, so if 1 upon, let us say 1 upon a plus ib is in the denominator, a plus ib is in the denominator, so we will multiply it by a minus ib in both numerator and denominator, so which is basically the conjugate of a plus ib, right? So in this question, conjugate of z will become, real part is 1 plus cos 2 theta, right? And conjugate will be minus sine I times sine 2 theta, right? Because if you can see that z was 1 plus cos 2 theta plus I sine 2 theta. So its conjugate will be 1 plus cos theta minus I sine 2 theta, right? And in the denominator, we will have z into z bar, z conjugate will be replaced by mod of z square, which is a real number. This is the benefit of multiplying with its conjugate, that denominator will become just the real part, right? So just like we did the rationalization of any number, right? We do not keep the square root in the denominator. So in the same way, we do not keep the imaginary number in the denominator, right? So this has been now replaced by a real value, which is the magnitude of z square, right? So magnitude of z, as you know, in the first part we have calculated as mod z was 2 cos theta. So mod z square will be 2 cos theta whole square, which is 4 cos square theta, right? So writing this as 4 cos square theta, right? So you can separate the real and imaginary part. Why we have to separate? Because it is asking about the real part only. So real part of 1 upon z. So that's why we need to separate the real and imaginary. So writing this as 1 plus cos 2 theta over 4 cos square theta plus imaginary part as sine 2 theta, not plus, minus. This is minus I sine 2 theta over 4 cos square theta, right? Now this real part we have to concentrate on. So again, using the double angle formula for 1 plus cos 2 theta, because in the denominator we have a single angle, means it is a half angle, and in the numerator we have a double angle. So obviously we have to replace this cos 2 theta with theta. So writing 1 plus cos 2 theta is 2 cos square theta. In the denominator we have 4 cos square theta. So it is just 1 by 2. And what is 1 by 2? You will write here the real part of 1 over z is half, which is a constant, right? And it can also ask that prove that the real part of 1 upon z is of the type 1 upon a, and hence find the value of a where a is any constant, right? So you can modify the question like this, and you can find out the value of a in that case, which has to be 2, right? It depends on whether it is asking for a as that constant, or it is saying 1 upon a as a constant. Fine. Okay, let us do another question like this, that this time the variable complex number z is given by this, where theta is lying between minus pi to plus pi. We have to show that mod of z minus I is 2, right, for all values of theta, and hence sketch in an Argand diagram the locus of points representing z, right. So in this case, this is z minus I, right, and originally the function is given as, not the function but the variable z is given by 2 cos theta plus I, so there is no I in this, right, but we can bring I, right, whatever is asked in the question, try to make that whatever is being asked. Okay, making means you have to form z minus I, because it is asking for the modulus of z minus I, right. So if you open up this, so z will be 2 cos theta plus I minus 2I sin theta, right, multiplying this I with both the terms inside the bracket, and now you can bring this I to LHS, right. So that will become z minus I, or just subtract I from both the sides, you will get the value of z minus I, right. So solution here in the first part, that z minus I will be equal to 2 cos theta minus I times 2 sin theta, right, and it is asking for the magnitude of this. So as you know, the magnitude is squaring the real part, which is 4 cos square theta, plus squaring the imaginary part, which is 4 sin square theta, and please do not square this I. Okay, if you square this I, if it is plus, then it will become minus. Had it been plus I 2 sin theta and you are squaring this I, that will become minus 4 sin square theta, so your question get wrong. So remember that things magnitude is just the, is a real number, so you have to take just the real parts, a square and b square. Do not involve a square plus ib square, right. So square root of this, so 4 you can take outside, it is just cos square theta plus sin square theta. You may use the identity, which is 1, so it will become 1. So z minus I mod is just square root of 4, which is 2, right. And then we have to sketch this diagram. This we have already done. Center is your I and radius is 2, right. So let me point out this. I means the y-axis and real part is 0. Please remember this, right. In the introductory video of this modulus, or the set of points in an Argand plane, when I was introducing this equation, z minus any complex number mod is equal to some radius, right. So there I mentioned that that can be a only real part, and that can be only imaginary part, right. So here is the case where the center is just a point which is lying on the y-axis, its real part is 0, right. So this point is basically 0 comma 1, right, in terms of Cartesian coordinate, right, and its radius is 2. So if this distance is 1, this distance is 2, so this has to be the radius, and you can take out the circle. Let me try. Okay, so this has to be the center, and this has to be the radius. Okay, roughly, right. So this is your circles, and it is intersecting at this point, which is 0 comma minus 1, because this distance has to be 2. This is 1, this has to be 1 because radius is 2, right. All right, and all these z will lie on the boundary R, on the boundary of the circle. So this is your region R, right. Second part is prove that the real part of 1 upon z plus 2 minus I is a constant. So again, just like we did in the previous question, since this z plus 2 minus I is another complex number, so we have to bring this in the numerator by multiplying this complex number with its conjugate, right? So, and then separating the real and imaginary part, right? So it is in the second part, and this is basically 1 over z plus 2 minus I. So z minus I we already have in the first part, which is 2 cos theta minus I 2 sin theta, and here we have to add 2, right? So it will become 1 over 2 cos theta plus 2, because here 2 is added, which is the real part. So real portion will be 2 cos theta plus 2, and again minus I times 2 sin theta. This is z plus 2 minus I, right? And multiplying this with its conjugate, right? So in the numerator, I am just writing in the numerator the conjugate value, right? So this will be 2 cos theta plus 2 plus I times 2 sin theta. Okay. All right. So in the denominator, we will have the magnitude of z plus 2 minus I. Right. So let us quickly find out z plus 2 minus I magnitude. Okay. In the denominator, right, which will be real part square, which is 2 cos theta plus 2 real part square plus imaginary square, which is 4 sin square theta and square root, right? This will be 4 cos square theta plus 4 plus 8 cos theta plus 4 sin square theta. Okay, this 4 cos square theta plus 4 sin square theta will be just 4, because taking out 4 as a common factor, you will remain in the brackets cos square theta plus sin square theta, which is 1, right? So this is 4 plus 4 is 8, right? I'm just missing some steps, not missing, but just calculating the things in the mind, directly writing out this as 8 plus 8 cos theta inside the square root sign. This is z plus 2 minus I magnitude, right? So 8 again you can take outside. This will be 1 plus cos theta. Is it theta or cos 2 theta? 8 4 cos square theta plus 4 plus 8 cos theta. Yes, this is 4 cos square theta plus 4 plus 8 cos theta plus 4 sin square theta. 4 plus 4 is 8 plus 8 cos theta. Okay, right, and this is 1 plus cos theta square root, right? And this is the magnitude, right? And in the original question we have to find out the real portion of 1 over z plus 2 minus I, z plus 2 minus I real portion. This will be the conjugate of this, right, which is 2 cos theta plus 2 plus I times sine 2 theta, and in the denominator we will have the square of the magnitude, right? So square of the magnitude will be 8 times 1 plus cos theta, removing this square root sign, right? Now just take out the real part, which is 2 cos theta plus 2 over 8 1 plus cos theta, and the imaginary part is I times sine 2 theta divided by 8 multiplied by 1 plus cos theta, right? So real part of 1 over z plus 2 minus I is equal to, twice taking out the 2 as a common factor, you will get 1 plus cos theta. In the denominator we have 8 1 plus cos theta. So this can cancel with this. 2 by 8 is 1 by 4, which is a constant, right? So in the previous question we were getting the constant as 1 by 2, and in this case we are getting the constant as 1 by 4, right? Same thing you can, or the question may ask for the imaginary part. If imaginary part is somehow coming out to be constant, So it will ask for the imaginary part, right? Okay, let us do one more question. Uh, it says that a complex number 2 plus I is denoted by u, its complex conjugate is denoted by u star. Show on a sketch of an Argand diagram with origin O, the points A, B and C representing the complex number u, u conjugate and u plus u conjugate respectively. Describe in geometrical terms the relationship between the 4 points O, A, B and C. Right. So, if I take the complex number as 2 plus I, okay, let me change the background. Okay. Right. So, Z is 2 plus I, right? This is 2 plus I. This is our Argand diagram, Argand plane, sorry, not just the diagram yet. So this is not Z, it is basically U, replacing this with U. So U conjugate will be 2 minus I, and it is also asking for U plus U bar, right? So U plus not U bar, U plus U conjugate will be, imaginary part will get cancelled out, so you will just get 4, right? So we have 3 points. One is 2 plus I, so this is 2 plus 1I, so this is your U, right? Then we have U by 2 minus I, so 2 minus I will be U conjugate, just a reflection in the real axis, and U plus U bar is U conjugate is just 4, so here we have 4, right? And if you join all these points, you will get an equilateral triangle. Not equilateral, you will get an isosceles triangle. Right? You can name this point as A, B and C, because this distance is equal to this distance, right? We cannot say that this is an equilateral triangle because this distance, which is basically, this is 2 and 1, this point is 2 and minus 1, so this BC distance is 2, right? And this is 2, so CA distance is 2 root 2. 2 and 2 is 4, 4, 2 root 2, yes. Right, so we cannot say that this is an equilateral triangle because side lengths are different. Yes, definitely they are. This is an isosceles triangle, right? AB and AC will be equal. Right, so this was your A part. Fine. Now it says that express U and U conjugate in the form x plus IY, where x and y are real. Right, so U and U conjugate. So again, since U conjugate is in the denominator, right? So U by U conjugate, you can multiply this by U. So in the numerator it will become U into U, and in the denominator it will be U conjugate into U, which is just, this is U square by mod of U square, because U into U conjugate is mod of U square, right? So since U is 2 plus I, so this is 2 plus I whole square divided by mod of 2 plus I, right? So let me separately calculate mod of U, which is 4 plus 1 square root, which is 5 square root, right? So mod of U square is 5, right? So this is 5, right? So U by U upon U conjugate is 2 plus I whole square divided by 5. So again separating into real and imaginary part. So this is 4 plus I square is minus 1 plus 4I divided by 5. So separately writing with this with a different color, you have u by u conjugate now as 3 by 5 plus I times 4 by 5. Right, this is your real part, this is your imaginary part. Now it is asking where x and y are real. So x value is 3 by 5 and y value is 4 by 5. Now it says by considering the argument of u by u bar, u conjugate or otherwise, we have to prove that tan inverse 4 by 3 is equal to twice of tan inverse 1 by 2. Now, before proving this, if I talk about any complex number of the type z, which is of the type a plus ib, right, and its conjugate is a minus ib, right, and z by z bar, if I'm talking about the argument of this, right. So just remember this, that first you can say that it can be proved also that z argument of z by z bar is twice of, means this is argument of z minus argument of z conjugate, right, and argument of z conjugate is negative of argument of z, right, because in the complex plane, if you plot this, suppose this is your point z, okay, which is of the type a plus ib, and it is like this, and this is making an angle theta, right. So this distance is a, this distance is b, right. So this is point a plus a comma b, right. So its complex conjugate is given by just a mirror reflection in the point in the real axis. So this will be your z conjugate, where this is b and this is a, and this angle will be theta. But this time this theta you are measuring with the positive x-axis with the real axis, but in this time you are measuring in clockwise direction. This theta will be given by minus theta, so its exact value will be minus theta, right. So if you talk about argument of z, is basically its magnitude will be theta, but its value will be minus theta, right. So it will be twice of argument of z, because this will become minus theta. So argument of z is theta minus argument of z is z conjugate is minus theta, so it is just twice of theta, right. So in the given question, if I have to prove, let me clear up this. Okay, so here we are, it is 2 theta. So u by u conjugate is 3 by 5 plus I 4 by 5, and its argument of u by u conjugate is tan inverse 4 by 5 divided by 3 by 5, which is basically tan inverse 4 by 3. This is your left hand side, right. So tan inverse 4 by 3, this is the argument of u by u conjugate, right. So according to this rule, that argument of u by u conjugate is basically argument of u minus argument of u conjugate, which is twice of argument of u, right. So argument of u is tan inverse, imaginary part is 1 and real part is 2, so it is 1 by 2, right. So this is tan inverse 4 by 3, right. And if we have to prove that why this is, how this identity come, that argument of z minus argument of z conjugate, you can prove this also, but in some another lecture I will prove this, right, not this time, right. So just practice all the questions that we have already covered, and if you have any more doubt or any question that you need to discuss in some video, so just write in the comment section. I will make a separate video, right, and explaining that question. Okay, so that's all for now. See you in the next video. Till then, bye, take care, see you soon.